Hello everyone, welcome to this week's video. This week's slides were produced by Nirajan, so if you happen to see him, tell him thank you. Okay, our next lab is going to be forces. In the past, we've looked at some of the most basic principles in physics: position, displacement, velocity, and acceleration. Now we're going to be looking at one of the most important concepts in physics, forces. Okay, for this lab, we have several objectives. These are the things that you should be able to do by the end of the lab. 1. Identify the forces acting on a system. Draw a free body diagram. Relate the mass of an object to its weight. And identify and predict the direction of normal forces, frictional forces, tension forces acting on an object. Okay, one of the first things that you will need to learn when dealing with forces is how to build a free body diagram. This is really important. You're going to be using it for every single physics class you're going to take from now until you graduate. So, free body diagram. To draw a free body diagram, first be clear about your system. What is the system? Is the system a beam in a bridge, or is it the bridge itself? Whatever the system is, you need to be able to state it and state it explicitly. Then identify all the forces acting on the system. These are not forces by the system, but are acting on the system. The representation, just put a dot. That represents your system. You could draw a picture if you would like, but often we just use a dot. And draw all force vectors pointing away from that dot. For example, let's consider a brick on a ramp as shown in this figure. So what is the system? The system is the brick. What are the forces acting on the system? Well, 1, we have the normal force on the brick by the surface. We have frictional forces on the brick by the surface. We have gravity, the force on the brick by the earth. Now put a dot for the system and draw all the forces pointing away from that point. Now notice the labeling convention that you have a force acting on an object by an object known as FAB. So here, we have N, which is the normal force on the brick, B by the surface, S. Or the frictional force on the brick by the surface. So it's FBS, WBE. Pay really close attention to this, this notation that we use. You're going to want to use it on any diagrams. Actually, anytime that you note forces, use this system of notation because things will start getting really messy soon. And this will help you keep everything nice and organized. Okay, so now we're going to draw a free body diagram. There's your dot. There's your normal force. There's your frictional force. And there is your weight. Okay, now we're going to look at what types of forces there are. First, there's the contact force, which is a force that exists only when two interacting objects are in contact. For example, friction, tension, spring forces, normal forces are also a contact force. Then there are non-contact forces, and those don't require there to be any kind of contact with the system. Gravity is one. Do you need to be touching the earth for gravity to work? No. Magnetic forces, if you've ever tried to push two magnets, two north poles of a magnet together, you know that they don't have to be in contact for there to be that force. Also, the electric force is another one that could be on this list. Magnetic force, electric force are ones that you will look at next semester if you take physics next semester. Okay, so commonly encountered forces mechanics are weight. The force with which a body is attracted towards the earth. So there is how we would represent weight. Gravity on an object is always towards the center of the earth. In other words, it's always pointed downward, and this is a non-contact force, which will come be more important later. In our labs, we are going to use this little thing we call a force probe to measure these forces. Okay, weight and the mass of an object are related with the following relation: weight equals mg. So weight in newtons equals the mass in kilograms times the acceleration due to gravity, which is 9.8 meters per second squared. All right, so here is another type of force, the tension force. And that is the force developed in a string, cable, chain, rod, or any continuous object due to its weight or external force. Tension, think of a rope. It's always pulled. Here's some tension. Here's another example of tension. And this is another example of tension that you will have to solve a problem probably in lecture like this. Right, here's a bowstring that's under tension. The chain on the swing is under tension. Okay, here's the string and some spring under tension. Okay, light string or rope. The tension is the same at every point. This works for a very, usually we say a massless string or a massless rope. Something that's really small, maybe we'll use something really thin like a nylon string, fishing line, something. So you can say that the tension is the same at every point. It's very important that you remember this. The tension is the same at every point in the string. Now something like a chain, this is very different because it's heavy and you have each point in the chain is having to carry all of the mass of the chain below it. So as you go up, the tension will increase, but that's not something that you'll have to worry about in this lab. Tension is a contact force. That is very, very true. All right, so now we're going to talk about normal force. The normal force is acting normal to the surface of an object that is in contact. Normal force is always perpendicular to the surface in contact. Okay, so here's our system. There's your normal force. It's pointing up. Your normal force is pointing over to the right. You notice that it is perpendicular to the surfaces in contact. But the ball, there is no normal force because it's not in contact with anything. If the surface of is our system, then the normal force on the surface due to the ball is shown in this figure. There you go. Normal force on a surface by the ball and the weight of the ball are two different forces. They are only equal and opposite whenever they are on a flat surface. So in the case with the ball on the flat surface, the weight and the normal force would be the same. But of course, on the slanted surface, this is not the case. The normal force, of course, is a... All right, our next force is the frictional force, which refers to the force generated by two surfaces that contact each other and slide against each other. Frictional force always opposes the direction or tendency of motion. So if the object is already moving, friction will be the opposite direction of your motion. If the object is not moving, like say like the brick on a slanted surface, but if the brick is not sliding down the surface yet, it's going to be the opposite of the tendency of motion, which would be if there was no friction, which direction would it go? And then the friction would point in the opposite direction. Okay, here we have a couple of cases. There's another case where friction would be. Friction depends on the nature of the surfaces, the smoothness, roughness, and the materials in contact. Skis on snow, of course, is going to give you a whole lot less friction than tennis shoes on grass. If you have something heavier, you're going to have more friction than if you have something lighter. Frictional force and normal force are related by the following relation. Friction equals mu n, where the friction is the frictional force, n is the normal force, and mu is the coefficient of friction. If mu is 0, then we're dealing with a frictionless surface. Friction, of course, is a contact force. Okay, now to end this slide, here are some things to think about. And these are things that you should be able to talk about on your RAT. Let's see here. For a light string, is the tension the same at all points along the string? How does an increase in mass affect frictional forces? For that one, look at the formula for friction. How do normal forces always point up? If not, how are they related to the surfaces they contact? Can you state the convention used to note forces? If you have any questions about these, it would be a good thing to talk to a tutor or talk to your TA. But we're good to go, so see you guys next week. See you later. Bye.